So in this case, we have the integration values. So this integration value of 9.1, I'm going to divide everything by 9. That in turn gives us relative integration values of 5, 2, 2, and 1. But this integration value looks a little off. So we'll see if that has any relevance later on. I'm going to calculate the du value now. So I take 2 times the number of carbons plus 2 minus the number of hydrogens divided by 2. That in turn gives us 8/2, or a du value of 4. From here, let's draw some fragments. This chemical shift of around 7, that suggests we have an aromatic ring. The integration of 5 suggests we have 5 protons. Okay, we have a triplet with an integration value of 2. And another triplet with an integration value of 2. And we have a singlet with an integration value of 1. Okay. This chemical shift of around 4.0 suggests a hydrogen attached to a carbon adjacent to an alcohol. This broad singlet suggests an alcohol. And this peak at around 3, that's probably going to be a benzylic position with 2 hydrogens. Now, because we have a triplet, and we have a pair of triplets, that suggests that these 2 protons are adjacent. So what I'm going to do is I'm going to draw these proton fragments, and I'm just going to connect them. So I have my benzylic protons. I'm going to connect them to the protons adjacent to our carbon attached to the alcohol. And that in turn gives us our set of triplets. This also explains our singlet, and it explains the 5 hydrogen multiplet. The du value of 4 calculated also matches this structure. So with that, we have all of our peaks assigned and accounted for. Okay, let's keep going now, and let's do another example. In this case, let's try to draw a structure matching the following proton NMR spectra. So pause the video, work through this example, and then we'll discuss. So in this case, let's calculate the du. We have 2 times 4 plus 2 minus 6/2. That in turn gives us 4/2, or a du value of 2. In terms of the integration values, this suggests we have a ratio of 1 to 1 to 1. Considering that we have a triplet and a triplet of triplets, this suggests that we have 2 hydrogen fragments. So we have 2, 4, 6 hydrogens accounted for. You can also reason it by the fact that 3 hydrogens times 2 gives us 6. So I just multiply all of the hydrogen counts by 2 so that the total number of hydrogens match the number of hydrogens in our formula. Okay, so this 2 hydrogen fragment at around 4 suggests a proton that's attached to a carbon adjacent to an alcohol. Okay. Considering that this is a triplet, it's adjacent to something else. Okay. We don't likely have an alkene present or anything like that. And these peaks around 2.5 and 2.0 suggest something like a proton adjacent to a carbonyl group of some sort. Okay, what we can determine as well is this triplet of triplets tells us that we have a CH2 group that's adjacent to another CH2 group that's adjacent to a second CH2 group. That would explain why we have a triplet of triplets, a triplet, and another triplet. Okay, so let's now try to square this circle a little bit. In this case, one of our protons is adjacent to an alcohol, or at least a carbon attached to the oxygen atom, and another of our protons is adjacent to a carbonyl. Now, we don't have any extra atoms. We already used up all of our atoms, but this is not a valid structure. Because we have a du of 2, and this structure only has a du of 1, let's make a ring now, and let's in turn get it so that our du value matches the calculated du value. From here, we can just check this proton with a chemical shift of around 4.5 as a triplet would match this proton here. This proton, that's a triplet of triplets with a chemical shift of around 2.2, would match this signal here. And our last triplet with a chemical shift of around 2.5 matches this signal here. So as you can see, we drew out our fragments, we connected our fragments, and in this case, because the du didn't match, we made a ring so that the du that we calculated matched the du for our structure. Wonderful. So let's keep going now. What we're now going to discuss is carbon NMR spectroscopy, specifically carbon-13 NMR spectroscopy. To be clear, carbon-13 is the only carbon isotope with nuclear spin. The natural abundance of carbon-13 is 1.1% of all carbons in molecules. As a result of this low natural abundance, carbon-carbon signal splitting is not observed. Further, to get reasonable signal to noise, signal averaging and Fourier transform NMR is employed. Here's what a carbon-13 NMR spectra looks like. Under normal carbon NMR spectra collection, broadband decoupling is employed and CH coupling is not observed. You'll just see a series of singlets in a traditional carbon NMR spectra. Many scans are collected and averaged to achieve a reasonable signal to noise, in part because carbon has such a low relative abundance. So for those wondering, why should I collect a carbon NMR spectra? The carbon NMR spectra identifies the number of chemically unique carbon nuclei and the chemical shift of each carbon nucleus. Carbon NMR spectra do not report integration, but they're nonetheless incredibly useful for identifying and differentiating carbons. Oftentimes, carbon NMR spectra are collected along with proton NMR spectra. As you can see, in this case, we have 5 unique carbons, and thus we see 5 unique signals. And we can differentiate those carbons based on their chemical shift. As a reference, here is an appendix of chemical shift values for carbon NMR spectroscopy. In general, carbon is deshielded by electron withdrawing groups. So you'll see carbon signal shifted downfield to the left if there are electron withdrawing groups attached to or adjacent to your carbon atom. It's important to note that for carbon NMR spectra, the ranges of chemical shift values are much broader than in proton NMR spectra. In general, more substituted carbons will be shifted farther downfield, with quaternary carbons being the farthest downfield to the left and primary carbons being the farthest upfield to the right. Just like before, I would encourage you to have this chemical shift appendix handy and available as we go through these next discussions. Now, before we take a look at any carbon NMR spectra, it's important that we talk about chemically unique carbons. So a signal is only observed for a chemically unique carbon nucleus. Carbon nuclei are chemically identical if they can be interconverted via rotation or reflection across a plane or axis of symmetry, or via rapid bond rotation on NMR timescales. So for example, if we take a look at the following molecule, we see that there's a clear axis of symmetry, and thus there are 1, 2, 3, 4, 5 unique carbons, and thus we see 5 carbon NMR signals. It's important to note that the carbon atoms must be interconvertible via an axis of symmetry. For example, in this dibutyl ether, we only see 4 signals because there's a clear axis of symmetry. If we shift the oxygen atom 1 atom over, the carbons are no longer interconvertible via an axis of symmetry, and thus we see 8 signals. As practice, let's take a look at these next 2 compounds, and let's in turn identify how many unique signals we would see. In this compound, we have a clear axis of symmetry, so these 2 carbons would appear as 1 signal. This carbon would appear as a unique signal. This carbon would appear as a unique signal, and this carbon would appear as a unique signal. In total, we would expect to see a total of 1, 2, 3, 4 signals. By comparison, if we look at this compound, these carbons are not equivalent. The reason being is across this alkene, we see that one of these carbons is cis to our aldehyde, while the other carbon is trans. Thus, we would see 1, 2 unique signals for these 2 carbons. We'd see a 3rd signal for this carbon, a 4th signal for this carbon, and a 5th signal for this carbon, for a total of 5 unique signals. 1, 2, 3, 4, 5. So with these examples in mind, I'd like you to try to take a look at the following, and I'd like you to tell me how many carbon NMR signals would you expect to see for each of the following compounds. I'm going to do the first example, and you'll tackle the next few examples. So, the reason why I'm wanting to handle these first 2 examples is they cover pretty unique points in terms of interpreting carbon NMR spectra. So first and foremost, taking a look at this structure doesn't contain necessarily an axis of symmetry, but more an axis of rotation. What that means is that if we rotate this molecule, what we find is that the carbons on each side of this axis are equivalent. And as a result, in this molecule, we would expect to see 1, 2, and these 2 carbons would be treated as the same signal. So we'd see a total of 3 signals. The second example, looking at this transalkene is also pretty informative. When we're thinking about unique carbons are not interchangeable via rotation. However, what we see is these two carbons are in fact interchangeable via rotation. If we rotate this molecule, essentially if we wanted to draw this axis, we're essentially rotating this molecule 180 degrees vertically and then 180 degrees horizontally. And as a result, these two carbons are equivalent and would be one signal. Likewise, these two carbons are also equivalent via rotation, and thus we would expect to see two signals for this compound's carbon NMR spectra. So it's always important to check for axes of symmetry and rotation. So, with those examples in mind, I'd like you to approach these next examples and tell me how many unique carbon NMR signals would you expect to see for each compound. So pause the video, work through these examples, and then we will discuss. Okay, so let's work through the following example. So in this case, we have a clear plane of symmetry, and thus these two carbons are equivalent. And we have a second chemically unique carbon attached to the carbonyl group. Thus, we would expect to see two carbon signals. Looking at this next compound, there is a clear plane of symmetry. So we have 1, 2, 3, 4, 5 unique carbons. So we'd expect in turn to see 5 unique carbon NMR signals. For this last compound, again, there's a clear plane of symmetry. That in turn means these two methyl group carbons are equivalent. Likewise, these two carbons are chemically equivalent. These two carbons on each side of the plane of symmetry are equivalent. And these two carbons are equivalent. Thus, we would expect to see a total of 4 signals. So as you can see for carbon NMR spectra, you have to be on the lookout not only for axes and planes of symmetry, but also for interconversions via rotation. So let's do some practice regarding carbon NMR spectroscopy, and let's assign the carbon-13 signals for methyl propanoate. So in this case, we are given the carbon-13 spectra, and let's assign each carbon to each peak in the carbon-13 NMR spectra. So pause the video, work through this example, and then we'll discuss. So the first carbon I'm going to focus on is this carbon attached to the carbonyl. This carbonyl carbon has a chemical shift of around 180 part per million. Next, the carbon that is attached to an oxygen atom has a chemical shift somewhere around 50 part per million. So I'm going to label this proton B, and that matches this signal. The proton that's adjacent to the carbon attached to the carbonyl will be the next most downfield. We'll label this as proton C. And the least substituted methyl proton would be the most upfield, so this would be proton D. So with that, we've assigned each proton in this carbon NMR spectra. Let's look at another example. Here, I'd like you to assign carbon-13 signals to each unique carbon in the following structure. And I have a list of each unique carbon in the following structure. And I'd just like you to note that there are 1, 2, 3, 4, 5, 6, 7, 8 unique carbons. So, pause the video, work through this example, and then we'll discuss. So, first things first, I'm going to start with the easy ones. So this carbonyl carbon, this aldehyde carbon, is showing up at around 190 part per million. Generally, the carbonyl carbon is the easiest and fastest to identify. Next, what we're going to do is we're going to look at these aryl group carbons. This molecule contains a plane of symmetry, and as such, we only have 1, 2, 3, 4 unique carbons. One moment. Okay, so an aryl carbon will show up somewhere between the range of 120 to 140. An alkene carbon shows up around 110 to 130. I'm going to get one of the easier carbons to assign out of the way, this methyl group carbon. Sorry, let me label this as carbon A. So this methyl group carbon that I'll call carbon B is going to be right here. From here, in terms of the chemical shift values, we would expect the alkene carbons to be shifted a little farther downfield than usual because we have this electron withdrawing group. Given that we have a pretty clear set of two signals in the 140 to 160 range, these two signals here, I would expect these two signals to match the alkene carbons, which I'll label as carbon C and carbon D. So I expect carbon D and carbon C to be here. And then these protons will match the aryl carbon. Sorry, these carbon signals will correspond to the aryl carbons, which are over here. We have 1, 2, 3, 4 signals corresponding to the 4 aryl carbons. So with that, we were able to assign each peak in this carbon NMR spectra to a unique carbon found in this compound. It's important to note that carbon NMR spectra are usually not taken in isolation. They're usually taken in combination with the proton NMR spectra. So as you can see, we can use the chemical shift of each carbon to assign the identity of each carbon in the NMR spectra. Let's now talk about a variant of carbon NMR spectroscopy known as DEPT NMR, or distortionless enhancement by polarization transfer NMR, which can be used to differentiate carbons based on substitution. So in DEPT carbon-13 NMR spectroscopy, the carbon NMR spectra is collected and all carbons are visible. As you can see in this case, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So we have 1, 2, 3, 4, 5, 6, 7, 8 carbon NMR signals. Next, a DEPT 90 spectra is collected where only CH group carbons are visible. So DEPT 90 is selective for CH carbons. This is why, for example, when the DEPT 90 spectra is collected, only these two carbon NMR signals are observed. One corresponding to the alkene CH carbon, the other corresponding to the alcohol CH carbon. Next, a DEPT 135 spectra is collected, where CH3 and CH groups appear as positive signals. So in DEPT 135, your CH and CH3 groups appear as positive signals, while CH2 groups appear as negative signals. Tetrasubstituted carbons, or quaternary carbons, do not appear. As we can see here in the following molecule, we see all of the CH and CH3 groups appear as positive signals. We can also tell that these signals that are new in the DEPT 135, but not present in the DEPT 90, these are CH3 carbons. By the same token, the negative signals that appear are the CH2 carbons. So DEPT NMR spectroscopy allows you to differentiate carbons based on their substitution patterns. Now, how do we go about interpreting DEPT carbon-13 NMR spectra? In combination, the carbon NMR spectra, DEPT 90 and DEPT 135 spectra, allows all carbons to be differentiated based on their substitution. The way that you do this is first you check the DEPT 90 spectra. That identifies all the CH carbons. Next, the DEPT 135 spectra will identify all CH and CH3 carbons as positive signals and all CH2 carbons as negative signals. Finally, the broad carbon NMR spectra allows the tetrasubstituted carbons to be identified. So here's a summary of the signal patterns for DEPT carbon-13 spectra. One variant and one type of test that's commonly run as a quick alternative to DEPT NMR spectra is the attached proton test, APT. In the APT test, CH and CH3 groups appear as positive signals, while CH2 and quaternary carbons appear as negative signals. The attached proton test is a useful alternative if you don't want to run a series of DEPT carbon NMR experiments. So our CH and CH3 carbons are positive, and the CH2, as well as the quaternary carbons, appear as negative signals. Okay, let's keep going. Let's do some practice now interpreting DEPT carbon-13 NMR spectra. So we have the carbon-13 NMR spectra, the DEPT-90, and the DEPT-135 spectra. Here we're asked to determine the structure of an alcohol with the formula of C4H10O given the following NMR spectra. So in this case, we see we have 1, 2, 3 unique carbons. From the DEPT-90, we know one of the carbons is a CH carbon. From the DEPT-135, we see another carbon is a CH2 carbon. And this carbon here is a CH3 carbon. So with that information in mind, we see we have a CH3 carbon. We have a CH2 carbon with a chemical shift of around 70, which means it must be attached to some sort of alcohol. And we have a CH group with a chemical shift of around 30. Additionally, we know that one of these carbons, there is an equivalent carbon. There must be some sort of axis or plane of symmetry. Checking the formula of C4H10O, that gives us a du of 4 times 2 plus 2 minus 10 over 2, or a du of 0. So we don't have any carbonyl groups, etc. So in this case, what this suggests is we have a CH2 group. It's attached to an alcohol. We have a CH group, and then we have a CH3 group. In this case, in order to generate an axis of symmetry, we likely have two identical CH3 groups. This in turn gives us the following proposed structure for this molecule, which matches both the number and the chemical shift of each of the carbon NMR spectra signals. Let's do another example. So in this case, I'd like you to determine the structure of an alcohol with the formula C5H10O that exhibits the following carbon-13 NMR spectra. Of note, no signals were observed for the DEPT-90 spectra. So I'd like you to pause the video, work through this example, and then we'll discuss momentarily. Okay, so in this case, no signals in the DEPT-90 spectra tells us we have no CH carbons. Okay, the DEPT-135 tells us that this signal here is a CH2. This signal here is a CH2. And these two signals are CH3s. There are no quaternary carbons. We see also there's this signal here, and that is our quaternary carbon. The chemical shift of around 210 also suggests it's a carbonyl carbon. Checking our du, we have 5 times 2 plus 2 minus 10 over 2, which gives us 2 over 2, or a du value of 1. So in this case, what this tells us is we have 5 carbons, and we have 1, 2, 3, 4, 5 unique signals. So we have 5 unique carbons. So we have a carbonyl group, and then we have 5 unique carbons. So here are some possibilities. in terms of how we arrange the carbonyl group. We can immediately rule out this possibility because it has an axis and plane of symmetry, and thus we would only see 3 unique signals, not 5. Looking at this next compound with the aldehyde, the problem with the aldehyde is that this carbon is not quaternary, and as a result, we would see a CH carbon signal in the DEPT 90 spectra. So we can rule this one out as well. Thus, the only remaining option would be the following compound. Let me make sure it has 5 carbons. 1, 2, 3, 4, 5. It has 5 carbons and a carbonyl group. It has 2 CH3 carbons, 2 CH2 carbons, and 1 quaternary carbon. So this structure matches all the requirements and matches all the peaks observed in the DEPT 90, the broadband, and the DEPT 135 spectra. Wonderful. Let's keep going now. And let's talk about integrated practice involving proton NMR and carbon NMR. So in this case, we're asked, what is the structure of a compound with the following proton NMR and carbon NMR spectra with the formula C9H10O2? So let's work through this example. So pause the video, work on this example, and then we'll discuss this example momentarily. Okay, so first things first, what you're going to do first and foremost is to calculate the DU value. So C9H10, that gives us a DU value of 2 times 9 plus 2 minus 10 over 2. That gives us 10 over 2, or a DU value of 5. Now I'm going to start breaking apart the proton NMR spectra. This chemical shift of approximately 12 suggests a carboxylic acid. These 5 hydrogens with a chemical shift of 7 suggests an aromatic ring with 5 aromatic protons. From here, these 2 hydrogens each suggest we have a methylene group. One of the methylene groups is likely adjacent to a carboxylic acid. One of the methylene groups is likely adjacent to the aromatic ring. In terms of unique signals, we see in the carbon NMR a carboxylic acid carbonyl carbon. We also see 1, 2, 3, 4 aryl carbons. And we see 1, 2 alkyl carbons. So in this case, we see we have 1, 2, 3, 4, 5, 6, 7. So we have 7 unique carbons. Okay, let's take a few moments now and let's try to put together our fragments. Based on coupling, these 2 CH2 groups are going to be adjacent to one another. So that in turn tells us we have the following CH2 group adjacent to the carboxylic acid CH2 group. Okay, that in turn yields the pair of triplets From here, we have a total of 1, 2, 3, 4, 5, 6, 7 unique carbons, which contributes the 7 carbons observed in the carbon NMR spectra. And thus, the chemical shifts observed in the proton and carbon NMR spectra match the following compound. Let's do another example, and let's talk a little bit about structural characterization. Structural characterization often utilizes multiple sources of data, either collecting the proton, carbon NMR, along with IR, and other data such as mass spectrometry. One thing I'd like you to note, if the sample is a solid and a crystal can be prepared, X-ray crystallography is a powerful modern tool for determining the structure of organic molecules. You can take a grown crystal, collect the X-ray spectra, and in turn create a reasonable model to assign the structure of your organic molecules. Really powerful technique. In terms of a general guide to structural characterization, when you characterize the structure of an organic molecule, you'll often collect multiple pieces of data, be it multiple spectra such as IR, proton and carbon NMR, mass spectra, elemental analysis, and if needed, 2D NMR spectroscopy. When you're assigning the structure of a compound using this collected data, you can use the mass spectra to identify the molar mass. You can use elemental analysis to calculate the formula. From the formula, you can calculate the degree of unsaturation, and you can use the FTIR spectra to identify major functional groups, only considering those allowed by DU. From here, you can use the proton NMR spectra to assign the connectivity of hydrogens and their attached atoms, and you can use carbon NMR spectra to verify the carbon connectivity. Finally, if needed, you can use DEPT 90 and DEPT 135 NMR spectroscopy to verify carbon substitution. It's important to note often we aim to determine the structure of reaction products, so we can use our chemical knowledge to estimate and predict the possible products and their spectra. For example, if you're converting an alkene to an epoxide, you know that you will have an alkene proton in the reactant, while the epoxide proton will have a different chemical shift in the product. You can also note that the reactant will have a CC double bond stretch in an IR, while the product will have a CO single bond stretch in the IR spectra. Okay, so let's do some practice. This time, I'd like you to assign the structure for a compound with a formula C5H10O given the following data. So we have the IR spectra, we have an NMR spectra, proton NMR, and we have the carbon NMR spectra. So pause the video, work through these examples, and then we'll discuss. Okay, so first things first, taking a look at the mass spectra, I'm going to shelve that for now, and I'm going to focus on seeing first, looking at my formula, what is my DU value? So we have 5 times 2 plus 2 minus 10 over 2. That gives us a DU value of 1. Looking at the IR spectra, it looks to me like we have a peak past the 3000 mark, and we have a peak at around 1600. So it suggests we may have a carbon-carbon bond, such as an alkene. Okay, let's take a look at the proton NMR. We have 3, 4, 5, 6, 7, 8, 9, 10. So all of the protons are accounted for. We have a 3-hydrogen triplet, a 2-hydrogen quartet. So that suggests these 2 protons are adjacent. A 2-hydrogen doublet, a 2-hydrogen multiplet, and a 1-hydrogen multiplet. These protons in the chemical shift range value of 5 to 6 would correspond to alkene protons. This suggests we have some R group and 3 alkene protons. Okay. Continuing on with this analysis, we have a peak around 4.0, which suggests this methylene is adjacent to a carbon attached to an alcohol. This peak of around 3.5 also suggests a methylene group adjacent to a carbon that's attached to an alcohol. Okay. Putting together our fragments, we have a CH2 group that's adjacent to this CH3 group via coupling. So that tells us we have an oxygen adjacent to an alcohol, and that CH2 group is adjacent to a CH3 group. On the other side, we have another CH2 group attached to a carbon attached to an oxygen. And considering this splitting pattern is a multiplet, it is likely that these two protons are adjacent. So what that tells us is we have a vinyl proton that is adjacent to these protons that are adjacent to the carbon attached to oxygen. Why? This CH2 group is a doublet, while this proton is a multiplet. Okay, let's check the carbon NMR spectra. The carbon NMR spectra supports the evidence that we have 1, 2 alkene carbons. We also have 1, 2 carbons attached to an oxygen atom. And our fifth carbon is just like a CH3 group carbon. So here we have 1, 2, 3, 4, 5 atoms. So that gives us a final assigned structure that looks like so. So as you can see, we used our degree of unsaturation to give us a ballpark of what functional groups we had. We in turn use the IR spectra to flag any major functional groups. In this case, an alkene is present and there's an sp2ch bond. From here, we checked the integration and multiplicity in our proton NMR, and we noticed that because we have protons that have related splitting patterns, those protons must be adjacent. The CH2 and CH3 group are adjacent, and this vinylic proton as well as this proton adjacent to this carbon-oxygen bond must be adjacent because this proton is a doublet, which means it's only adjacent to one other chemically unique hydrogen. This in turn yields the following structure, which we in turn verify matches our proton and carbon NMR spectra. Let's do another advanced example. This time, I'd like you to assign the structure for a compound with the formula C4H8O3 given the following data. So here's the IR, you have a proton NMR, and you have a carbon NMR that is available with DEPT 135 and the proton decoupled spectra. So pause the video, work through this example, and then we'll discuss momentarily. Okay, so in this case, first let's calculate du. So we have 2 times 4 plus 2 minus 8 over 2. That in turn gives us 2 over 2, or a du value of 1. Ooh, that's a broad peak. That may be an alcohol, but we notice that we also have this peak around 1700, which is the CO stretch. So that tells us that this peak is a carboxylic acid. So we have a carboxylic acid present in our molecule. That explains the du value of 1. Okay. Um, or we have a carbonyl and an alcohol. That's another possibility. The reason why I reconsidered is because if we take a look at the proton NMR, this peak with a chemical shift of around 3.8 corresponds to an alcohol proton, and that's supported by the fact that it vanishes in a D2O wash. Okay, looking at the expansion of this, we have a singlet, we have a quartet, and we have a triplet. Okay, this triplet is likely a CH3 group. This quartet's a CH2 group. This singlet, I'm not sure yet. Okay. This peak that is positioned around 4.5 suggests that we have a CH2 group attached to a carbon that's attached to an oxygen atom. This peak around 3.4 suggests we have an alcohol. We also have an isolated peak that is around 4.0, which suggests we have an isolated CH3 group attached to an oxygen attached to a carbonyl group. So based on coupling, the triplet and quartet hydrogens are adjacent to one another. We also have, and we're also able to reasonably conclude that we have some sort of ester like carbon, which would appear as the singlet. It's unclear based on integration if it's an ester that looks like this or if there's something else at play. We're going to need to take a look at the carbon NMR spectra for a little bit more information. So in this case, looking at the DEPT 135 spectra, we have a CH or a CH3 group, and we have 1, 2 CH2 groups. In the proton decoupled spectra, we have a single carbonyl group. And we have 1, 2 carbons adjacent to an oxygen, and 1 carbon that's just on its own. Okay, because we have 1, 2, 3, 4, we have 4 unique carbons. Looking at the formula, C4H8O3, yeah, that makes sense. In this case, we know that we don't have a ketone. This chemical shift of around 170 tells us that we have an ester or carboxylic acid. Given that we don't see a peak around 10, we don't have a carboxylic acid, we just have an ester and an alcohol. So in this case, if we draw out our ester, we have 2 CH2 groups and a CH or a CH3 group. This would be the CH3 group. Okay. So let's start with a fragment we can definitively determine. We definitely have a CH3 group attached to a CH2 group attached to an oxygen. This is the signal that's the quartet of around 4.5, and this is the triplet of around 1.2. From here, this could also be this oxygen could be attached to the ester carbonyl or something else. From here, we have some sort of singlet, and then we have an alcohol peak. This singlet appears around 4.2, which matches a carbon attached to, which matches a proton attached to a carbon attached to an oxygen. That accounts for 1, 2, 3, 4 carbons. We have one CH3 group and 1, 2 CH2 groups. And we have the carbonyl quaternary carbon. So even though we don't have the integrations, we can use the multiplicities to note adjacent protons. The DEPT 135 spectra tells us we have two CH2 groups, and this structure matches the number of CH3 and CH2 carbons. So this gives us a final structure for this molecule that looks like this. The key thing is we were able to detect the presence of a carbonyl group using the IR spectra and verify that using the using the carbon NMR spectra. We can confirm that we have an alcohol instead of a carboxylic acid by virtue of the fact that we have the alcohol proton chemical shift, and we can verify that proton belongs to the alcohol because it disappears during a D2O wash. So as you can see, you draw out plausible fragments, and then you connect those fragments together to generate your final molecule. So that concludes our discussion of chapter 11, which focuses on NMR spectroscopy, proton and carbon NMR spectroscopy. With this, we've covered all the major methods of structure characterization, and you should be comfortable looking at proton, carbon NMR spectra, as well as IR spectra, and using that data to assign and determine the structure of organic molecules. That concludes this lecture for the chapter 10 this concludes our chapter 10, chapter 11 lecture series focusing on spectroscopy and structure characterization, and we'll continue and move on now in future lectures and begin discussing concepts regarding aromaticity and aromatic reactions.